Hi, my name is Sam Ibrahim, and my student ID is 222124112. Here's my student ID. Hopefully that's visible enough. Yep, so this video is for assignment one, part one for algorithms and data structures. I'll walk through each task in the notebook and explain how I approached the problems, why I made certain choices in my code, and show that it is running correctly. I'll just share my screen. Perfect. Okay, so this is a new I restarted the session, which means that I will have to quickly get the data. Um, okay, great. So the first thing that we do is define the word class in task one. So it defines the word object by first making everything lowercase, starting each word with a frequency of one, and the neighbors field is empty, but that'll be filled in later on in the task. Um, yeah, uh, the and this is used because we want to store words and their properties, especially because it makes tasks later on in the assignment a lot easier, especially things like sorting and comparison. It means that rather than uh, juggling plain strings and recalculating the length repeatedly, um, we can wrap things up in a class. So next we move on to creating the lexicon and reading the data files. That's task two. So what this does is it first defines the lexicon as a dictionary, and then it reads the data, strips any white space, and uses the word itself as the key. What it then does is that the value of the word object, the value is then the word object that we just defined. So this means that I can quickly reference any word later on, if needed, which I found incredibly useful in writing this code because I could check specific words, usually at random, to see if it's running how I would expect it to. So I'll just run that quickly, and that didn't work because I forgot to run first section. There we go. Yep, and so here we can see the first few entries, and we can also see that it's not sorted. Because we have an A word before, uh, after an I word. So yeah, next we have the interesting part of the task where we get to choose an algorithm and define it. I chose the bubble sort algorithm. It's pretty simple. It's pretty effective. It's one of the first things that we learned. Um, what it does is it takes the word list or the word object list and it repeatedly compares adjacent pairs. So if it compares them and if one is longer than the other, then it swaps. Um, and if it's not, then it doesn't swap, and it just sort of continues this as it sort of iterates through the list again and again and again until there are no changes, and then that means that the list is sorted. Um, so I'll just run that, which defines the bubble sort function. The next one is a little bit more complicated. This is a hybrid sort function, which is sort of made up of two sort of sub-functions, if you want to call it that. The first is the insertion sort, and the next is the merge sort. Um, and here it's pulling on each one depending on whether or not the length of objects is higher or lower than a threshold. This is something useful to do in cases such as this because you don't always know how big the data set that you're going to get is going to be. And there are different data sets, sorry, there are different algorithms that are useful for different sized data sets. For example, the bubble sort is really easy to put together, but it's incredibly inefficient for really large data sets, which is actually um, what we're dealing with here today. So I set the insertion sort threshold at 16, which means that if the if the number of objects is less than 16, it'll use insertion sort. If it's higher than 16, it'll use merge sort. Yeah, so we'll just run that. Awesome. So that's now defined. So what we'll do now is we'll move onto here, which tests the amount of time that each one takes. So we can do that by quickly, I'll set the benchmark with the bubble sort, um, and it'll go through it 5 times and give us an average. So we'll just give that a second. Awesome. So that's given us 3.1 seconds. So next I can swap that for hybrid and we'll be able to see the difference. Yeah, so it's 0.01 seconds. So it's many multitudes faster to use the hybrid sort, which in this case, because of the size of the data set, would have been the merge sort. Um, yeah, so next what happens is task 4 is that we're going to be sorting the lexicon um, using a the algorithm chosen by a user, actually. So if a user inputs 1, it'll bubble sort, and if they input 2, it'll hybrid sort. Um, yeah, so what we'll do is we'll run that, and I'll choose 2 just to be interesting. Yeah, and it seems to have done that really well. So it shows that there are 728 instances of the letter A. The neighbors are still empty because we haven't gotten to task 5 yet, which is what we'll move on to now. Um, yeah, so this is the task where I think things get really interesting. We're finding the nearest neighbors for a word using edit distance. Um, so the way that it works is that it matches words based on length, and it sees how and it calls two words neighbors if the number of differences between the word is exactly one. Um, so that one letter difference. And then it adds those words to the neighbors. So I'll just run that, and that seems to have worked. So next what we're going to do is the a simple part of the task, which is that we're just going to output the data that we've just made, the sorted data set that we've just made. So we'll run that. Great. And we should be able to see this by going here and finding the out text file. Perfect. So as we saw before, for A here, there were 720 instances, but now we can see all of the neighbors that A has, which, as you would expect, are all just letters, but that continues all the way down. Perfect. Thank you for watching.